Good evening, and congratulations to Jesse and Alex and Dr. Britton for their awards. And I want to thank the committee, and in particular Mark Hyde, for inviting me to give this talk. Mark asked me to be reflective and provocative, and so I spent a little time doing a Google search on the Heimlich maneuver, since I knew it was a banquet speech and I might actually have to help people out. So this is a talk, it'll take a little while, it's a little sciencey, but please bear with me because I think a lot of the things that I'm going to say are going to tie together some of the things that you've heard at the conference and some of the things that you've been reading and hearing about and put it in a little bit different context. So it's going to move fairly quickly, and the reflection part of it is that along with my BFF Tom Swetnam, we attended this conference in 1997, in October of 1997 in Park City, Utah, on the future of wildland fire science. And it was a very interesting conference. It was run by facilitators at a time when neither I nor Tom could stand facilitators. And they were doing a lot of interesting stuff that neither one of us were really comfortable playing with, but we went ahead and did it. There were a few things that we were asked to do. One was imagine and dramatize changes in the wildland fire community that will have taken place by October 2010. And we were asked to sort of weigh in on what we were prepared to do to achieve this vision ourselves as individuals. And then we were asked to design a story, a play, or some other creative way of communicating this vision, at which point there was a gagging reflex of what it was that we were being asked to do. And so Tom remembers all the details that I'm getting ready to tell you, and he told me that evening that I had embarrassed myself. So what I did was I actually hung, I went over and found a janitor to give me a piece of cardboard. I cut it out into a TV screen, and I sat behind the TV screen, and I did the newscast. I was the news anchor. And in take one, this is what I said. This was fire season 2002. Mind you, this is 1997. And I'm reporting that in the middle of this, worst drought in 50 years, I'm sitting there praising the federal government for having taken advantage of these prior wet decades to pursue an aggressive program of prescribed burning in the urban-wild interface. So that was take one, and in take two, I was taking the opposite tack. And you'll see by the end of my talk why this is actually significant, because I think we're on the verge of this once again. So it went pretty much over people's heads. They had no clue what I was talking about. It sounded crazy. I made a fool of myself, and I can't even remember what Tom's skit was. It wasn't good. So in this conference, we came up with some action plans to be implemented. One was create an interdepartmental competitive grants program, which actually became the Joint Fire Sciences Program. Create a coordinated response to managing fire regimes for ecosystem health. Create an environment for research and management collaboration. Integrate social science expertise and assess ecological risk. And I've got to say, looking back on it, we can be critical about a lot of stuff, but when I look at just the sheer volume of things that have happened since 1997, I'd have to give this talk kind of on a congratulatory note. I mean, I think there have been lots of tools built. There's been tremendous science done. I actually decided not to do this, but I actually collected what I thought were seminal papers. If you're interested, I'll be happy to send you a list. Since 1997, there's truly been a lot accomplished, including a lot of prescribed burning, a lot of fuels treatments under the National Fire Plan. And so I think a lot has been done. This is a very vibrant community. It's not a community where you'd say, particularly in the science community, it's not a community that you would berate for not having prioritized the science. I think the science has been prioritized. You could argue that the translational part of it has not been as good, and of course, in part, that's why we have a Southwest Fire Consortium, and we have these regional consortia. It's basically affixed to the fact that a lot of the science was not basically translated and put into action. So I'm going to take a little trip through memory lane. It's a little bit of navel gazing, but you'll excuse me. And I'm going to go through some things that I was involved in, right about this time, or actually over the last 15 years. And right at about that time, in 1997, Craig Allen, Sue Cannon, John Moody, and Deb Martin and I actually instigated a series of field visits across the West to basically promote the idea of doing the necessary science to address the whole issue of fire effects on watersheds. And it was a time where we could see the spate of fires that were coming, and we were concerned that the original reason for the National Forest, which was to protect watersheds, was going to be violated by the things to come. And I've got to say, this is one of the points in my career which I would argue was a real failure, in the sense that I got very frustrated and pretty much bailed out. Other people in that group kept doing science focused on fire effects on watershed. I didn't see the money coming, and I wasn't going to do it on a dime. And I ended up actually turning around, writing a series of proposals, and working for the next 12 years, reconstructing the environmental history of the Atacama Desert in northern Chile. A lot of times, this is about the accidents and personal history. It's whether you take a left or whether you take a right, and whether you take responsibility. In that particular case, I did not. The next thing I want to talk about is something that I've been working on throughout my career, which is decadal variability in climate, particularly in the Pacific and the Western Americas. And for a number of years in the early 1990s, I actually chaired and convened a workshop called the Pacific Climate Workshops, PACLIME. And in 1995, I wasn't running it then, but we had one of our meetings was actually on interdecadal climate variability over the Pacific and Western Americas. And Tom Swetnam and I wrote a really nice paper on mesoscale and decadal scale variability in the American Southwest that appeared in Journal of Climate. And I've got to tell you this just brief story that this was kind of a turning point. In 1995, the North Atlantic, which had been relatively cold since about 1960, turned warm. And we were all wondering what was going to happen when the Pacific actually turned cold, be the perfect ocean for drought. And so a lot of the rest of my career, I spent a lot of time sort of looking at these ocean influences on climate variability and ecosystems. And so I'm going to talk a little bit about that. In 2004, after about 5 or 6 years of people telling me that buffalo grass was going to end up being a huge problem and that I should help them actually deal with it in southern Arizona, and I should take leadership because nobody else was. And I've been sitting up on top of a hill on Tucson's west side for almost 30 years, and that I should actually help out with this. There wasn't anybody at the University of Arizona that would take that responsibility, or in the federal government, and that maybe I could do something. This is another accident in personal history. I actually kind of refused to do it. I said all for one for all, or not at all. And then I came to realize that not at all was not an option. It just so happened that the Kinder Morgan gas pipeline, the petroleum pipeline running from El Paso to Phoenix, actually burst into it through the ecological reserve that I helped manage. And so, to make a long story short, I extorted the pipeline company for money to start this outreach and demonstration project in buffalo grass that ended up becoming a nonprofit. And I'll talk a little bit more about that because I think it's a really good template for how you might do this across jurisdictions. And what I'm worried about is that this is a nonprofit. Economic downturns, down profits actually suffer. And so what you see is the glue across jurisdiction actually becomes unglued during these economic downturns. And then in 2005, shortly thereafter, I decided that we couldn't address climate change without actually having a national phenology network, a wall-to-wall continental scale network where we were making observations about the recurrent events in the annual life cycle of plants and animals. And we didn't have one. It was amazing. We were like the third world of phenology. I mean, the Europeans had one, but we liked one. And so I went on this journey. You can already see that my, my obituary is going to read, paleoecologist buried in Chaco Canyon, eulogy all about tilting at windmills. But anyways, I've come to appreciate really how much of an impact changes in seasonal timing in the future are going to have on everything that we're talking about, from snowpack to fires. So I'm going to start kind of heavy, because I think if you haven't heard this before, it's important to hear it. At decadal timescales, the Atlantic Ocean, particularly the North Atlantic Ocean, and the Eastern Pacific, actually the whole Pacific, modulate climate variability. And this is part of the internal variability in the system. It's going to happen no matter what. It's not going to go away. It's been happening for thousands, if not tens of thousands of years. It's going to continue. We need to understand it. It's going to continue under climate change. And so in the two pictures up above, you're looking at the first principal components of sea surface temperature that's been smoothed and detrended. And you can see the patterns for something called the Atlantic multi-decadal oscillation, where you get, these colors are not warm and cold, they're just patterns of opposition in the two different colors, in the blues and the reds. But you can see this sort of monotonic, uniform behavior in the North Atlantic. And then you can see the behavior of the Indian Ocean and the tropical Pacific for the decadal variability in the Indian and the Pacific Ocean. And it's not one or the other, it's that both of these oceans, all of these oceans actually end up modulating climate variability on these decadal timescales. And so when you think about climate variability, you have to think of the interaction of things like the Pacific decadal oscillation and the Atlantic multi-decadal oscillation. And when you look at them at the continental scale in terms of the hydroclimatology that they affect, you can see things like in the bottom two left maps, where a cold Atlantic with varying the Pacific decadal oscillation will give you patterns where it's generally wet, and then you switch the wet and dry places from the Pacific Northwest to the Southwest, depending on whether the Eastern Pacific is warm or cold. And the reverse is true when the North Atlantic is cold. So again, remember the statement that I made, that in 1995, we were sitting there on the verge of seeing big changes with the North Atlantic actually turning warm, and expecting the whole continent to go dry like it did during the 1930s and 1950s drought. And I would argue that maybe we're right now on the verge of actually seeing it go the other way. In other words, for the North Atlantic to get cold and the tropical Pacific to actually get warm. And it may actually get wet sooner or later. So this is important because it affects so many things. This is a signal that's actually transferred through ecosystems. And so much so that we've been able to actually reconstruct the Atlantic multi-decadal oscillation from tree rings on both sides of the pond, on both sides of the North Atlantic, places like Africa, the Middle East, and Scandinavia, in the eastern US. And on the upper left is a reconstruction that we did, that somebody just redid, but with trees from Siberia and China. And you can take our reconstruction and overlay it on theirs, and they're exactly the same. This is a huge, persistent pattern, and what you're actually looking at is are the upper air dynamics being influenced all across the northern hemisphere. And that's why the hydroclimatology is affected across large continents. Now, in North America, one of the interesting things that happens is since the Atlantic multi-decadal oscillation can modulate both temperature and precipitation, it can modulate things like fire activity. So Thomas Kitzberger, Tom Swetnam, and others actually published a paper where they looked at the influence of the Atlantic multi-decadal oscillation on the asynchronicity and synchronicity of fire across Western North America. And you got these sort of patterns where you can see the influence on whether or not fire is actually synchronous across the West or asynchronous across the West in areas that normally behave in opposite fashion from north to south. So when the north is wet, the south is dry, and vice versa. So this has got to be something else. It either has to be the scale of the drought and wet patterns of the droughts and the pluvials, or it has to be operating through some influence of sea surface temperatures on actual land temperatures, and possibly something like phenology or seasonal timing. So that's something that I've been working quite a bit on as background for beginning the National Phenology Network. And what I'm getting ready to show you is an index that we can actually calculate for any weather station that has daily Tmax and daily Tmin. And it's an index of spring onset that is validated with lilac and honeysuckle data that goes back into the 1950s at the continental scale. So we have this index that we can basically map out for the whole US over the whole 20th century, over the last 100 years, and then look at what's happening at the continental scale. What is happening from the picture on the left, and these are trends in spring inset, is that most of the US, over most of the US, the spring has actually been advancing, but in the southeast, it's actually been delayed. And we're talking about an advance of 4 to 8 days, counterbalanced by a delay in about 4 to 8 days. And this pattern is actually part of the internal Pacific variability. So this is not climate change. This pattern of opposition is likely to continue into the future. This is probably the first time you've ever heard anybody mention a term called the warming hole. And this is where the temperatures are not warming as rapidly as they are anywhere else. And this is in the southeastern US. And there's a tremendous amount of research going into this right now with modeling. At the bottom right corner, in the red, you have the time series of spring onset mapped at the continental scale. So it's a time series running from 1900 to 2010, and you can see the step change right in the 1980s. You will see the step change over and over and over again. We've had a major change that was relatively abrupt between 1976 and 1984 that speaks to everything that we've been hearing, from changes in spring onset to losses in snowpack, to earlier snow melt, to the increase of rain over precipitation as you go up the mountain, to earlier stream flow. These are all the things that you've been hearing about, and it's that step change right there. And it's mostly driven by the western US, where in fact the spring has advanced abruptly about 8 to 10 days on the average. The blue line is the southeastern US, and you can see the step change right in the 1950s. That is not climate change. And in fact, what's happened is you've had a delay in spring onset, roughly about the same, in this case about 4 to 8 days. And it has to do with changes in the mid-tropospheric flow that is driven by internal Pacific variability. The reason that I'm going through this very carefully is that I want you to understand that climate variability is the one opportunity that we really do have. And decadal variability is extremely important, because when we miss those opportunities, as I pointed out in my little crazy skit, when we miss those opportunities, they may not come back for another 20, 30 years. And so we have to be poised to do stuff if in fact the weather turns wet for a decade or two. We have to be ready to put stuff on the ground as fast as we can. So we're doing lots of stuff, lots of research, trying to sort of tease apart what these patterns in spring onset are, because they're so important to everything that we're talking about, from our water supply to the fate of our ecosystem as driven by fire and other disturbances. So one of the studies that we just published was looking at the relationship of ENSO, of El Nino Southern Oscillation, which is more of an interannual variation, and the Pacific Decadal Oscillation, this internal Pacific variability, because both of those are what we call in statistical terms temporally autocorrelated, meaning they're lagged by months, meaning that they set up as early in the fall, and they may be, so in the fall you may actually be able to predict what's going on in the spring. So that may give us forecasting capability on things like annual area burned, if in fact temperatures affect the frequency of large fires in the western United States. So we're trying to figure out ways of actually forecasting the onset of spring and perhaps forecasting things like fire activity all the way to wheat harvest. So I think that Craig Allen and probably others have shown the figure on the left from the Westerling et al. Paper that came out in 2006. Tom Swetnam was a co-author on that. I think it's one of the seminal papers in our field, in the field of fire climatology. And you see the relationship of those bars, which are the frequency of large fires that exceed 1,000 acres or 400 hectares over time, and then plotted as the spring and summertime temperature. And you can see this relationship that's relatively close, and then you can see that inflection point right at about 1984. In the middle, you've got correlations of the number of fires against the center of mass. Now, the center of mass is a hydrological term, and that's when more than half of the mean annual stream flow passes the gauge. In other words, the snowmelt pulse. And so you're looking at the correlation, which is positive just about everywhere. You don't see very many blue dots on those maps, which would mean a negative correlation. And then the size of the dot is the strength of the correlation, and these are calculated for all our stream gauging stations in the USGS network. On the right-hand side is our spring index correlated against the number of fires for the whole western US in the top. Sorry, I didn't mention this. And then for fires in the southwest in the bottom. And you can see that it doesn't matter whether you use center of mass or spring onset from this algorithm that we created that you can map out for stations that have daily Tmax and Tmin. The patterns are generally basically the same. If you have an early spring, it's an early spring for the most part all over the west. If you have a late spring, it's a late spring all over the west. And on a decadal scale, after 1984, the whole west actually had earlier spring onset. There's still variation around the long-term mean, but in general, the long-term mean has actually jumped up. So there is actually a very close correlation between these indices of both snow melt and spring onset and fire activity. So the reason that that's important is that it's driving so many of the things that we are talking about right now in Western North America. These are a series of metrics from top to bottom and from 1950 to 2000. And it starts with the spring index at the very top, then the wheat heading date. This is when the flowering part of the wheat plant actually emerges from the flag leaf, and it's something that all the wheat nurseries in the Central Plains record. So this is averaging across all the Central Plains station. The center of timing and stream flow, the number of fires exceeding 1,000 acres, the total area burned, towards the bottom, April 1st SWE, or snow water equivalent, and then at the bottom is butterfly phenology, when you get the emergence of butterflies in the Central Valley of California, which has been actually observed for a long, long time by a guy named Art Shapiro. And you can see the step change in all of these time series. We've had a major change that is being driven by this change in phenology, by this change in seasonal timing. And I guarantee that we don't really understand very well how this change is actually cascaded through Western ecosystems. And until we know that, we're going to have a hard time explaining how climate is going to affect ecosystems with future climate change. So we've been doing all kinds of studies. The paper that appeared in Science by Greg Peterson, who now works for USGS but was a student at the University of Arizona, and I was on his committee, This is a paper based on 66 tree ring chronologies from the northern and central Rockies. We call it the southern Rockies. These are about half of the chronologies were old, about half of the chronologies were created for this particular study. And so these 66 tree ring chronologies are used to reconstruct April 1st snow water equivalent. And that's mapped out in time series on the upper left time series with the northern watersheds in the blue and the southern watersheds in the red. And you can see right off the bat this pattern of opposition. In general, there's a lot of snowpack to the north when there's a lot of snow, when there's less snowpack in the south, and vice versa. Occasionally that kind of breaks down, but it really breaks down right around 1985 when both the northern and the southern watersheds basically start trending in the same direction. That's towards less snowpack. And what's happening actually is that in general, the north and the south, precipitation in the north and the south are influenced by Pacific variability in opposite fashion. And that operates at decadal to multi-decadal timescales. And what you're seeing in this is basically springtime temperature actually now replacing precipitation as the dominant influence on large-scale patterns of snowpack accumulation. This is pretty significant. So we're now actually teasing this apart. We're using a hydrologic model, a water budget model, to tease apart the influence of temperature and precipitation in two seasons, in the winter, November through January, and February through March. These are the different colors. I'm not going to go into a lot of detail, except to say that the blue colors are actually precipitation in those two seasons, and the warmer colors are actually temperature in those two seasons. The red is springtime warming, and the black in there is snow water equivalent, as modeled with this little water budget model. And so you can see the appearance of the red is actually February, March warming that's producing these big changes and are responsible for these big changes that I've been talking about all along. So now this is really significant because it's obvious that this is the kind of thing that could, in fact, drive fire activity across the West. But there are already projections from modeling that tell us that there's going to be a change in fire phenology. And this is a study by my friends and colleagues, John Abatsoglu and his wife, Crystal Colden. They came out in Rangeland Ecology and Management. And it was about looking at the influence of increased wildfire and the spread of invasive grasses. And so these three panels are basically multi-model mean projected changes by the mid-21st century compared to historical conditions. And so you're looking at the frequency of extreme fire danger, the advance in fire start season date, and the advance in median date of fire season. We're in trouble. I mean, there's going to be a change in the seasonality of fire, clearly. And that's going to be complicated by the fact that we also have invasive species in the deserts that are changing the climatology of fire in the West. So I've been really watching climatology advance at breakneck speed throughout my career. And 30 years ago, I used to do more hydrology and work with people who you would classify as probabilistic hydrologists or stochastic hydrologists, and then interacted with climatologists who all believed that a butterfly could flap its wings over here in the Pacific and influence something on the other side of the world. In other words, the climate system of the Earth is actually a fairly chaotic system, and more than likely doesn't have that much memory or persistence. And so a lot of climatologists and hydrologists ignored decadal to multi-decadal climate variability because that implied persistence. As a paleo guy, and all my colleagues who are paleo people here, we thought that was hogwash, but it was hard to shout down. And so for many years, we kind of grew up with the notion that, yeah, we could do seasonal forecasting, and maybe through greenhouse gases and big changes in radiative forcing, we might be able to forecast 100 years ahead. But this inner this interval in between, the decadal time scale, was very, very elusive. And actually, I think it's a very critical thing to get a hold of, because a lot of the adaptation to climate change is going to be at this decadal time scale. So now you read papers in Science and Nature. Here's one, Advancing Decadal Scale Climate Prediction in the North Atlantic Sector. The bottom one, Pacific Decadal Oscillation Hindcast, Relevant to Near-Term Climate Prediction. And we're on the verge of near-term predictability, of decadal scale predictability. And I guarantee you that as ecologists, we have not been thinking this way for 30 years. The goal of ecologists has not been, if we gave you decadal scale predictability in the climate system, could you actually do the ecological forecasting? That's not where the science has been headed for 30 years. In fact, far from it. And so now, we've got big questions. Economists are going to face this question. Social scientists are going to face these questions. Physical scientists are going to face it. If, in fact, we can predict the climate a decade or two in advance, do we know enough to forecast the fire dynamics, the successional pathways, and can we schedule fuels and post-fire treatments with those kinds of forecasts? And I think that's going to be a huge challenge, but it's coming soon. It could come in a matter of months, it could come in a matter of years, but it's coming soon. So one of the things that I've been trying to do in USGS with the science strategy exercises that we've been going through for a long time. It seems like we're doing these science strategies forever and not getting where we need to go. But one of the things that I've been suggesting is that in a matter of months, basically, that we assemble communities across different agencies and across academia, and basically write circulars, write reports on big challenges that need to be addressed at the national scale. And one of these is seasonal to decadal predictability of U.S. ecosystems and adaptive strategies. There is no such initiative now, but we're going to need an initiative. And even though we work in the Southwest and we're focused on fire ecology in the Southwest, we need to have a voice in these national initiatives. We need to push these national initiatives because they're really what are going to advance things that we're going to use in the next few years to decades. So with invasive species, I've been impressed by some of the advances that have been made. In fact, I set in on Matt Brooks and other sessions on invasives and was particularly interested to see what they were doing in terms of looking at climate variability, and particularly winter annuals in the Mojave Desert. And so generally, the way that you want to see this, and this is a paper from, this is also from a Batsablu's and Colin's paper in 2011, is that you have climate change and climate variability. It's affecting the potential range of the species, so you're looking at bioclimatic envelopes. The variability, the climate is varying. In fact, if you take red brome and you plot out a logistic growth curve through the actual data of the spread over the 20th century, the residuals of that logistic growth curve is actually the Pacific decadal oscillation. So the climate variability is going to very much impact the spread of these invasives as well as the fire activity associated with it, the changing fire danger. It's going to affect the establishment as well as alter the fuels and fire regime. It's going to alter the invasion potential and the wildfire potential. There are going to be feedbacks. This is a fairly complex issue. It's a big thing that is happening on Western landscapes that is apt to have huge impact, even though I think to a large part our focus is actually more upstairs in our woodlands and forests and less downstairs in the desert. But this is a fairly big thing that's happening with a number of invasive grasses, and there are a whole host of other grasses that are poised to also invade. It's not just these. So the winter annual grasses like schismus and red brome, cheatgrass of course, and in the south in the Chihuahuan Desert and the Sonoran Desert, also bufflegrass, which is something that I've been battling. So generally the logistic growth curve for these invasions looks like this. You have kind of a slow colonization phase, And then you have an expansion phase where you can really see the exponential spread of the species. Then you have a saturation phase. And with these grasses, at that point, then you're seeing fire kind of take over. And then fire is starting to drive a lot. So at some point, you're not really going to eradicate the grass when you're already into the control priority stage. And it's pretty much out of control by the time you're in the saturation phase and you're just managing fire. We all know this is the grass fire cycle. There's actually surprising little quantitative data for the grass fire cycle, but we talk about it as a conceptual framework for thinking about the impact of grass invasions on wildfire regime. So generally, you get these grass invasions filling in the space between the shrubs and the cacti, and then you have a fire, and it kills the native shrubs and cacti and other species, and then the grass comes back, the invasive grass comes back even stronger, and it's just this cycle, and pretty soon fire frequency, size, and severity increases, and you end up having tremendous impact to ecosystems and heightened fire risk. So basically, fire also has this logistic growth curve in the desert, and we see this big time because in the last few years, we've seen incredible fires. I mean, if you just take 2005 and you look at the Nevada fire complex that ran from Las Vegas to Utah, and you look at the Cave Creek complex north of Phoenix, those were two fires that burned over 1 million acres. I mean, that's pretty amazing. That's on the scale of anything that we see in our forest. And it's going to be really, really hard to control in the future. So really, we need to start asking questions, and Matt's group is doing a very good job of doing this. You know, can these invasives-driven wildfires start and spread anywhere, these big fires? Or are there central tendencies in time and space? Can we use these central tendencies to sustain treatments in the most likely areas to initiate these large fires? And probably the most important question here is, can we pool and bank resources from multiple jurisdictions to implement sustained treatments in these areas, regardless of which jurisdiction they're in? That's a really hard question. I've been working across jurisdictions in southern Arizona, and it's really literally like herding cats. It's very, very hard to do. So in southern Arizona, I've been working on buffalo grass. This is on the south slope of the Catalina Mountains in what used to be a dense Palo Verde saguaro forest, mostly below 4,000 feet on the south slope of the Catalinas. My kitchen window looks at patches like this, big yellow patches of buffalo grass that are, you know, knee-high and in some places higher, with saguaros that are embedded. Saguaros that are actually the last saguaros on the landscape, with or without fire. By the time that buffalo grass gets to occupy more than 43% of the biomass, there's a threshold, and you're going to get tremendous losses in biodiversity without fire. Buffalo grass is highly competitive for space, nutrients, and water. And so basically, ecosystem transformation is already occurring, even in the absence of fire. So we started in 2008. We started a nonprofit that's basically charged with coordinating the buffalo grass effort across jurisdiction. You could literally go to the Tucson Mall, the largest mall in the Tucson area, and yell buffalo grass, and you'd be amazed at how many people actually know what it is, which is part of the challenge. I think we've done a fairly good job with the outreach. We're trying to prioritize the science around this particular issue. My feeling is that buffalo grass and grass invasions and fire and climate change are all spatially extensive environmental problems that have a contagious quality to them. And so they're things that we're going to have to learn how to manage across jurisdictions. This is the challenge of the day, managing across jurisdictions. In southern Arizona, this is extremely complex because we have, we have national parks named after plants. We've got national monuments named after plants. We've got national forests. We've got BLM lands. We've got state lands. We've got county lands, we've got private land. It's a real mix, but it's also one of the richest, one of the most educated, and I mean, you've got a university there. If we can't do this in Tucson and in southern Arizona, we're gonna have a hell of a time doing this anywhere else. So part of it is doing what many of you do, which is sitting around with stakeholders and basically doing risk assessment, building tools, decision support tools, prioritizing the science. Instead of doing science willy-nilly, actually do the science that, thank you, the science that actually feeds into the management. As scientists, we pretty much want to be able to do whatever we want to do with the training that we've got, regardless of the problems in front of us. It's unfortunate, but that's the way it is. So we've done things like built vulnerability risk and priority assessments, map assessments for the Tucson Basin. We've also been doing a lot of research, a lot of focused research, for example, in the foothills of the Catalina Mountains, where in fact one of our PhD students actually set up a bunch of plots, used aerial photography, and actually mapped the rate of spread for buffalo grass at about 11 different sites, and did a bunch of other work at those sites that actually feed in to a state in transition model that allows us to basically run scenarios for alternative management strategies over the next 40, 50 years. And we just had a stakeholder meeting in Tucson where we actually did this. This is for the Catalina Mountains. We just did this for Ironwood Forest National Monument. So we ran these scenarios to show people what the outcomes would be if we just did nothing, or different levels of doing something. And we're now turning these into costs of doing nothing and cost of doing something. So this is becoming really interesting because it's so accidental, right? I mean, sometimes things happen that you can't really anticipate. We wrote a appropriations request to Congress. It got passed by the House, and then we had the midterm elections in the Senate, and the something that had already been passed by the House basically got tabled by the Senate. And in the process, this nonprofit lost about $1 million this past year. In the meantime, though, there was an opportunity for FEMA, and we actually wrote a proposal. The initial proposal was based on something else, and I said, you know what? I think this proposal will have a lot of success if we can actually show that buffalo grass actually impacts the interruption of essential services. When you fly into Tucson, it's an African flammable grassland. And so we ended up, for the county jail complex and for the airport, just got, in fact it was just approved yesterday, $3.4 million. Now, how many of these projects do you guys have that are $3.4 million? I mean, this is amazing. But it's so accidental and so haphazard. You know, it just really depends on the opportunity at hand and a lot of luck. So another initiative that not just USGS but everybody else might want to get involved in with a short fuse. And I know that Matt has actually worked on this for Forest Service publications, but I think we need to keep doing it. And that is an initiative in the West to look at grass invasions and altered wildfire regimes in American desert, and not just the science, but also the mitigation, with some realistic stuff. There's been a lot of science on this in the last decade, and I think it would be good to incorporate it, and this will raise it to the national level. So one of the things that I do is actually work on the fossil record. I work reconstructing not only vegetation history, but the history of plant migration in the West. And we've done this for a lot of the hallmark plants in the Southwest, pinyon pine, Utah juniper, things like ponderosa pine, creosote bush, and at fairly high resolution. And we've done this for pinyon pine, and I've always had a real interest on the set of outliers in the pinyon distribution, both for Pinus edulis and Pinus monophylla, over the last 40,000 years or so. And of course, in the last 40,000 years, the deserts were actually in pinyon juniper woodland and went to desert at the end of the last glacial period and the beginning of the Holocene. And at that point, these migrations of pinyon pine were triggered and they moved northward, but they've only arrived at the northernmost peripheral isolates very recently. In fact, many of them in the last 1,000 years. And so we've been going to a lot of these northern peripheral sites and determining the age of the stand using pack rat middens, and then coring the trees to determine the sequence in colonization. And it doesn't matter. I'm starting to come up with a disturbance theory of plant migration. And it goes like this. You have large-scale synchronized disturbance across the West, and then that opens up a lot of niches for recruitment. And in the wake of those synchronized disturbances, almost at the subcontinental scale, you end up either having the incumbent replace itself, or something that was rare, or something that's extra local coming in and becoming dominant. And this is, of course, something that we're set to see happen today, because we've had these the spate of large-scale disturbances, whether they're fires or bark beetle outbreaks, and we're really focused on the mortality, sorry Craig, kind of over-focused on the mortality and not so much on the succession. And I think it's going to be really important for us to start looking at the succession, because we're going to, more than likely, we'll start seeing weird things. We'll start seeing the spread of both native and non-native species to higher elevations and to the north. And so another initiative that we should be looking at, that in fact I think to some extent should supplant the Joint Fire Sciences Program. Controversial, huh? For those of us that have money that comes from Joint Fire Sciences. Excuse me. But that is an initiative that actually I mentioned in 1997, because I thought that to some extent we were kind of misplacing a focus on fire surrogates and the science behind fire surrogates. My argument was that a dozen years would pass by and very little of the science that we created, whether it was good or not, was going to end up being used to actually do field treatment. And so one of the arguments that I had is that we were going to see this spate of disturbances that was going to trigger things like migration, and that really the opportunity was for managing the products, engineering the products of succession. And it's not something that we've put a lot of effort in. In fact, we've put barely any effort into. We're going to manage the products of succession at the subcontinental scale. We may not want to accept that right now, but that is going to happen. It's going to happen sooner than we think. So I think having an initiative where we actually focus on managing the products of succession is going to be critical, because really we should have two objectives. One is to put fire and other fuels treatments on the ground to basically make these systems more resilient. But two, I think we have to be realistic. And if climate changes more than it's being predicted, we're going to end up seeing a lot of things happen really fast. And fuels treatments are not going to be the answer. It's going to be managing the products of succession when things are this tall, not when they're 40, 50, 60 feet high. So I was thinking of some news stories. I'm close to the end here. I was thinking of some news stories 13 years ahead, kind of like the challenge in 1997. And so I picked out a few things that I thought you might be interested in. So Boise, Associated Press, power industrial complex dismantled to reduce federal spending. Yuppies and survivalists abandoning the woods in droves. Tucson, Arizona, AP. Dozens of bufflegrass fire burn in the snowbird communities. Firefighters actually busy. Stop answering 911 calls for the elderly. Las Vegas. Nuke lab moved to Death Valley, where it should have been in the first place. Okay, so I'm just joking around, but I want to get serious and make some other projections. And so here are my uncalibrated projections for 2025, and you can take them or leave them. I think that the North Atlantic is going to turn cold and the Pacific is going to turn warm between 2014 and 2025. So what does that mean for us? It's going to be a wet southwest, a dry Pacific Northwest, and the spring onset is either going to be stable or somewhat delayed. The rate of summer warming will be slowed in the southwest. We're going to end up getting larger, more frequent fires in the southwestern deserts because the winters will be wetter. Fire will abate in southwestern forests, except those areas that are adjacent to non-native winter annual grasslands, which will be burning. And as a postscript, buffalo grass spreads as far north as Las Vegas and Truth or Consequences. So here are some other ones that have more to do with direct management. Now fires, which we've always reported either in terms of acres or now in square miles, I don't understand that, but in square miles burned, now are logged in dollars. And by dollars I mean suppression plus property loss plus the loss of ecosystem services. And I think that's the way that you drive the politics when you report that stuff in dollars and cents. With favorable climate and broad public approval, the government maintains a torrid pace of control burns since 2013. We may be upon this. Successional engineering replaces abandoned practices of post-fire seeding, restoration ecology, sorry Don, and assisted migration. Don agrees. The National Fire Forecasting Center, NIFC, called a godsend by Western Governors Association. Climatic forecasting and fire forecasting become really big. The USDA DOI Joint Ecosystems Program celebrates 10-year anniversary. And then a record 42 scientists and engineers were elected to the 127th Congress. Finally, on a very serious note, this was an essay that was written in Science by a friend of mine, Bill Schlesinger, who wrote that unless the discoveries of ecological science are rapidly translated into meaningful actions, they will remain quietly archived while the biosphere degrades. And I think that's dead on. I think academics, I think scientists may or may not be ready for prime time. And we may actually be able to document the demise of nature, but not do very much else. And it's going to be a challenge. It's going to require actually taking personal responsibility and shaking things up. And being provocative and being forceful and compelling. Thank you very much.